As we continue our discussion today of velocity, we're going to look at two different topics. The first is the difference between instantaneous velocity and average velocity. Instantaneous velocity basically just means what the velocity is of an object at one particular moment or one particular instant in time, whereas average velocity is the velocity over an entire trip. Now, average velocity is always going to be in between your highest and your lowest instantaneous velocities. So if you're going to calculate an average velocity and you find that it's not in between your highest and lowest instantaneous velocities, you'll know that you made a mistake someplace. The other thing that we wanted to hit pretty hard today is a discussion of a position versus time graph. Sometimes graphs are a little on the difficult side for some students to understand. So I want to go through some of the nuances of this position time graph with you and try to help you understand what it really means. So this particular position time graph, I'm going to have position on the y-axis with time on the x-axis, with position being measured in meters and time being measured in seconds. Now, it would probably look a little bit neater if I made this graph look more like, a lot of straight lines, maybe more like that. But the problem is that since we're talking about velocities, you can't just suddenly start running and be up to your top speed, or start pedaling your bike and suddenly be up to the speed that you're going to be at. It takes some time to speed up and it takes some time to slow down. So because of that, in place of having real sharp points on a position time graph, we tend to have more of a curve due to the fact that objects have to speed up and slow down. For some simplified versions, especially if you check out any of the extra problems on the websites that I gave you to look at, you'll notice that they have simplified things and they do have some nice straight lines. But keep in mind that in reality, it can't look like that because objects do have to speed up and slow down. They're not like the Roadrunner, if you've ever watched the Roadrunner on cartoons, where all of a sudden he comes up and he's flying at top speed and all of a sudden he just stops. Objects in real life can't do that because we're not cartoon characters. So that's why these curves are in here. Now, what's easier for me to do sometimes is to say, okay, what does this look like on the ground? What if I actually have an object that's doing this? What does it look like? Well, remember that we're talking about position, we're talking about displacement. So if I would get in a helicopter, or I get up and look out of a second story window on a person that's on the ground that's maybe generating this graph, it's going to look something like this. So if here is my 0 mark, or there always has to be a 0 mark someplace. 1, 2, 3, 4, it goes 5 meters this way, and then it goes 2 meters in the negative direction. So a -1, -2. Okay, so now it just looks like a simple number line, right? So this person starts out at 0, excuse me, and goes until he gets to a position of 2 meters right here. Then he turns around and he goes the other way and he goes back to 1 meter. Then he turns around and goes this way and goes all the way up to 5 meters. Then he turns around, he goes back past his starting point till he gets to a -2 meters. Then he turns around one more time and he goes up to where he gets back to a +2 meters. So if you draw something like this, it's a little bit maybe easier to understand when you first start, okay, what actually did this object do? Now, because we're graphing it up here with relation to time, we're going to be able to talk about how fast he did it, but here we're just looking strictly at the displacement. So if I want to look at the total distance that he covered, I would say, well, he went 2 this way and then 1 back this way, which makes 3. And then he went up another 4 to make 7. He went 7 back this way, which makes 14. And then he went another 4 this way, which makes 18. So his total distance was 18 meters. So if I would try to do the same thing on the graph, he went from here to 2, back to 1, so 2 plus 1 is 3. He went up to 5, so that's an additional 4 more. 3 plus 4 is 7. Then he went from 5 down to -2. 5 to -2 is 7 more, so 7 plus 7 is 14. And then from a -2 up to a +2 is 4. 14 plus 4 is 18. So total distance is 18 meters. But how far was his displacement? Well, his displacement, he started at 0 and he ended up at a +2. So in all of this going back and forth, his total displacement was only a +2 meters. Okay, so from a position time graph, you can certainly get distance and displacement, but you can also get some sort of idea how fast he's going at different parts on his trip. You should recall from algebra that you can find the slope of a line. And the slope of a line is defined as the change in y's over the change in x. And so in this particular case, my change in y is actually a change in position. And so change in position or displacement, we've defined that before as delta x. And my x-axis is a change in time. So I have delta x over delta t. That should look familiar because delta x over delta t is velocity, or v. Okay, so if I take the slope of this curve at any point, that's going to tell me what the velocity is, and specifically what the instantaneous velocity is at that particular point in time. Now, when you do this, you want to try to find a relatively straight portion of the curve, and kind of try to ignore the pieces where it's getting real curvy here. Now, what you can see is that from here to here, it looks like it's relatively straight. So from here, he's gone 1 meter in 1 second. So 1 meter divided by 1 second gives me 1 meter per second. Okay, so that's the slope of this line here, delta y over delta x. Okay, if I would look at maybe this portion of the graph, so at 4 seconds, he's about right here. At 5 seconds, he's about right here. So in this piece of the graph, he's gone from 5 meters minus 2 meters, because there's the 5 and there's the 2, and that's all happened over 1 second in time. So I have 1 second here. So over this portion of the graph, my velocity is going to be 3 meters per second. Now, if you look at this, you can tell that this piece of the graph is much steeper than this piece of the graph. So that tells us that the steeper the slope, the higher the velocity. When I get over here, now my slope is in the negative direction. And so remember that a negative velocity just means that he's going back the other direction. He's going back towards his starting place when he gets down to this part of the curve. You should also notice that when I get to a place like this one, or this one, or this one, or this one, what's happening there? Well, he's actually changing direction. He's going, here he's going forward, here he's going backward, here he's going forward, here he's going backward, here he's going forward again. So anytime where you have a curve and you have what's called an inflection point, that is going to indicate a change in direction. So all of those places are places where he changes direction. So if they ask you how many changes in direction there were, all you're going to look for is the top of a curve or the bottom of the curve, and you're going to be able to count that. So on this particular graph, you have a total of 4 changes in direction. Okay. If I know that my steepest slope is where my fastest speed is, if you look at this, where would you say the fastest speed is going to be? Well, it looks to me like probably the fastest place right here is going to be the steepest spot for this curve here. This one looks like it might be awfully close. If I actually calculated it out, I might find that they're really similar. Okay, so your steepest slope could be from here to here. It could also be on a negative portion of the graph. You can still have, if I'm talking about speed, it doesn't matter if it's positive or negative. So the steepest portion of the graph is always going to be your greatest speed. And the most unsteep, if that's a word, the most unsteep portion of the graph is going to be your slowest speed. Well, what's the speed at these inflection points? Well, if I would draw a tangent line right here, the tangent line goes like that. So the slope at that particular point is actually 0. So for a moment in time, at this point right here, he has a speed of 0 meters per second. So his velocity is actually 0 at that point, which makes sense because you've got to stop before you can change direction. So 0 meters per second here, here, there, and there while he is changing direction. Okay? So a couple of other points to make sure you get: the slope of a position time graph is going to be velocity. And if you change from a positive slope to a negative slope, that's also going to indicate a change in direction. Hopefully that will help as you practice interpreting position time graphs.